All right, so it looks like we're tackling AWS VPCs today. We got quite the mix of stuff here. Blog posts, official AWS docs, even some study notes. Someone's serious about this whole virtual networking thing.
Yeah, and for good reason. I mean, VPCs are kind of the backbone of pretty much everything you do in AWS.
Okay, so in this deep dive, let's try to unravel this whole VPC thing. We'll get into how they work, why it matters, and I think we should even uncover some of the quirky things we found along the way.
Oh, yeah, definitely some quirks. Like, did you know that AWS actually reserves 5 IP addresses in each subnet? Just one of those little details, that makes you go, huh, why is that?
Yeah, we're going to circle back to that one. But first, for anyone just starting out, let's break down what an AWS VPC actually is.
Okay, so imagine like having your own private data center, but in the cloud. That's essentially what a VPC is. It's a logically isolated section of AWS where you can launch your resources, you control your IP address range, subnets, routing. It's like your own little cloud kingdom.
My own cloud kingdom, haha. One of the sources we have here actually compared a VPC to a traditional data center, but with way more flexibility. And I'm
Wow.
starting to see why.
Exactly. You can spin up multiple VPCs, each one customized for like different apps or environments, and that level of control is just not possible with like a physical data center.
Okay, so if it's my cloud kingdom, I need some LAN,
Okay.
right? That's where I keep seeing this CIDR thing. What is that all about?
So CIDR stands for classless interdomain routing. Sounds complicated, but it's basically just a way to define a range of IP addresses. Every VPC needs a CIDR block. This basically defines its size, and you pick it at the beginning. So it's a decision you want to get right.
Okay, so I'm guessing you can't just change it on a whim later on?
Nope. Once it's set, it's set. Like laying the foundation for your cloud kingdom.
Yeah.
Choose wisely.
Foundations are important. And then we divide this CIDR block up further using subnets, right?
Right, subnets are like the provinces within your kingdom. They let you carve up your VPC into smaller, isolated networks, and you can control how traffic flows between them. This is super important for things like security and high availability.
High availability. I know that's a big deal with AWS. And I remember that subnets are tied to specific availability zones.
Exactly. AWS has these different availability zones, which are physically separate data centers. By putting your resources in different availability zones using subnets, you're protecting yourself from outages. So if one zone goes down, your application can keep running in another one.
Smart. It's like having backup castles throughout the kingdom. But here's a question. If subnets are tied to availability zones, does that mean once I create a subnet, I can't change its zone?
That's exactly right. You can't move a subnet to a different availability zone after you create it. You would have to create a new subnet in the desired zone and then migrate your resources.
Okay, so some planning is definitely required. It's like deciding where to build those castles. Once they're up, they're staying put. But how do we actually control the traffic between these subnets? You mentioned something about routing earlier.
Ah, yes, route tables. They're like the traffic cops of your VPC. They determine where traffic goes based on the destination IP address.
Okay, so if I want traffic from one subnet to reach another, I need to configure the appropriate route in the route table.
You got it. And it's not just about communication within the VPC either. We also need to think about how our resources talk to the outside world, like the public internet.
Right, because a lot of applications need internet access to function, but we also want to keep things secure. So how do we handle that balancing act?
That's where internet gateways or IGWs come in. They act as the bridge between your VPC and the public internet.
And I only need one IGW for the entire VPC, right?
Yep. It acts as a single point of entry and exit for all your internet traffic. But here's where it gets important. The main route table by default will send traffic to the internet gateway. So any subnet attached to that main route table will automatically be public.
Okay, that makes sense. We're starting to see the bigger picture now. We have our VPC, our CIDR block subnets in different availability zones, and route tables controlling the traffic flow. But what about security? Every kingdom needs its defenses, right?
Absolutely. And in the world of VPCs, we have two main lines of defense: security groups and network access control lists, or NACLs for short.
Security groups and NACLs, they sound kind of similar. What's the difference?
Think of security groups as like the personal bodyguards for your resources, like your EC2 instances, for example. They control traffic at the instance level.
Okay, so each instance gets its own security detail.
Exactly. And then you have NACLs, which are more like border patrol for your subnets. They control traffic at the subnet level, meaning they affect all the resources within that subnet.
Ah, so they're like different levels of security checkpoints. But I'm still a bit fuzzy on the distinction. How do they actually work differently?
It comes down to stateful versus stateless. Security groups are stateful, which means they remember the context of traffic. So if your EC2 instance sends a request out, the response is automatically allowed back in, even if you haven't explicitly opened a rule for it.
That's pretty clever. Simplifies things a lot. So no needs to create a bunch of rules for return traffic.
Exactly. The security group has your back. NACLs, on the other hand, are stateless. They don't track the state of connections. So you need to define separate rules for inbound and outbound traffic.
Got it. So security groups are like having a smart doorman who recognizes you when you come back in, while NACLs are more like those old-fashioned drawbridges. You need the right password to get in or out, no matter who you are.
Haha, I like that analogy. It really highlights the importance of having both. Security groups and NACLs work together to provide that layered defense, making your VPC that much more secure.
Layered defense. It's like those medieval castles with multiple walls and moats. You really have to work to get inside.
Okay, so we've got our internet-facing resources protected by security groups, and our subnets guarded by NACLs. But what about the resources that are tucked away in private subnets? They don't have direct internet access, right?
That's right. They're behind the castle walls, so to speak. But sometimes even those resources need to reach out to the internet, like for software updates or to access other AWS services.
Right, it makes sense. But if they're in a private subnet, how do they do that? Without exposing themselves directly to the internet.
That's where we get into the world of NAT gateways and NAT instances. But before we go down that rabbit hole, we have a little mystery to solve. Remember those 5 reserved IP addresses I mentioned earlier?
Oh, yeah. What is the deal with those?
Well, you'll just have to wait until part 2 to find out. Think of it as a little cliffhanger.
Ooh, I love a good cliffhanger. See you in part 2.
Welcome back.
All right, so are we ready to solve this mystery of the reserved IP addresses? I think so. So picture this, each subnet has these reserved IP addresses. It's kind of like those VIP seats at a concert, that are always roped off. You can't use them for your instances.
Reserved for the cloud gods, maybe?
Haha, not quite, but they do have important roles. The first 4 addresses are reserved for things like the network address itself, the VPC router, and DNS. They're essential for the subnet to function properly.
Ah, so they're like the behind-the-scenes crew making sure everything runs smoothly. But what about that 5th address?
So the last IP address in the subnet is reserved for network broadcasts. But here's the thing, AWS doesn't actually support broadcasting within a VPC, so it's more of a historical artifact.
Interesting. So it's there for legacy reasons?
Yeah.
But we don't really need to worry about it in practice.
Exactly. But knowing this helps you understand why you can't just use any IP address within your subnet. Those reserved addresses are there to ensure smooth operation of your VPC, and they prevent potential conflicts.
Mystery solved. I feel like I've leveled up my VPC knowledge already. But speaking of IP addresses, how do resources actually find each other? I know DNS plays a role there.
Right, DNS, the domain name system. It translates those human-readable names like google.com into IP addresses that computers understand. And within your VPC, this is handled by the Route 53 resolver.
Route 53 resolver, so it's like the phone book of our VPC, mapping names to IP addresses.
Exactly. And the great thing is you don't need to do any special configuration for your resources to use it. It just works.
Wait, really? How does that happen?
So every VPC has a Route 53 resolver at a specific IP address. It's always the point-to address of the VPC's first CIDR block. For example, if your VPC's CIDR block is 10.0.0.016, the resolver would be at 10.0.2.
So AWS automatically sets that up and makes sure all my resources can access it. That's pretty slick.
It is seamless and efficient. This ensures that your applications can connect to whatever they need, whether it's within your VPC or out on the public internet.
Speaking of the public internet, we were about to dive into how resources in private subnets access it. You mentioned NAT gateways and NAT instances.
Right. Let's start with NAT gateways. Imagine you have an EC2 instance in a private subnet. It needs to download software updates or access data from an external API. But it doesn't have a public IP address. That's where a NAT gateway comes in.
So it acts as a middleman, allowing the instance to initiate outbound connections without exposing its private IP address to the internet.
Exactly. The instance sends its traffic to the NAT gateway, which has a public IP. The NAT gateway then makes the request to the internet on behalf of the instance, and the response is routed back through the gateway to the instance.
That sounds pretty secure, but why would I use a NAT gateway instead of just giving the instance a public IP address?
That's a great question. It's all about security best practices. By keeping your instances in a private subnet and using a NAT gateway, you're reducing your attack surface. The instance itself is not directly accessible from the internet, so it's much less vulnerable to attacks.
That makes a lot of sense. It's like having a security guard screen all incoming calls before they reach your personal phone. You only get the important stuff. So a NAT gateway is a managed service right,
Yeah.
meaning AWS takes care of a lot of the setup and maintenance for me.
You got it. It scales automatically. It's highly available. And you don't have to worry about patching or managing the underlying infrastructure. It's a pretty hands-off way to handle outbound internet access for your private instances.
Sounds good to me. Less for me to worry about. But I do remember there was also something called a NAT instance, right?
Yes. A NAT instance is essentially an EC2 instance that you configure yourself to perform NAT. It's a more hands-on approach. You're responsible for things like instance size network configuration and operating system updates.
So it's more like building your own internet router.
Yeah.
Instead of using a pre-configured one, I can see how that would be more work.
Exactly. And AWS actually recommends using NAT gateways over NAT instances whenever possible.
I'm guessing there's a good reason for that.
There are actually a few reasons. First, NAT gateways are designed for high availability and scalability. They can handle a lot more traffic than a single NAT instance, and they automatically scale up and down as needed. Second, NAT gateways are much easier to manage. You don't have to worry about all the operational overhead that comes with running an EC2 instance. And finally, NAT gateways are more cost-effective in most cases. Especially if you have a lot of traffic, you only pay for what you use.
All right, I'm sold on NAT gateways. They sound like the way to go for most scenarios. So we've covered how to get private instances online, but what if I want to connect different VPCs together? Like if I have multiple applications running in separate VPCs, can they talk to each other?
They can, and there are a couple of ways to do it. The simplest is VPC peering.
VPC peering, it sounds like a friendly gathering of VPCs.
Haha, in a way it is. VPC peering lets you create a private connection between two VPCs, making them act as if they were on the same network. It's all private, no internet or public IPs involved.
Well, it's like a secret tunnel between our cloud kingdoms.
Exactly. And it's a great way to enable secure communication between applications running in different VPCs. You can even peer VPCs across different AWS accounts, which is really useful for organizations with multiple accounts. However, there's one important thing to keep in mind. VPC peering is non-transitive.
Non-transitive. Now that sounds like a math term.
Yeah.
What does that mean in the context of VPC peering?
Think of it like having separate phone lines between your VPCs. Just because VPC A can call VPC B and VPC B can call VPC C, it doesn't mean that VPC A can directly call VPC C.
Ah, I get it. So each peering connection is a direct one-to-one relationship. No automatic daisy chaining.
That's right. If you want to connect multiple VPCs in a chain, you would need to create separate peering connections between each pair.
Okay, that's important to remember. So VPC peering is great for connecting a couple of VPCs. But what if I have a more complex network with lots of VPCs? Or even multiple AWS accounts? Is there a better way to handle that?
There is.
Yeah.
And it's called a transit gateway. But before we jump into that, let's talk about another important security consideration: controlling outbound traffic from your VPC.
All right, we're back for the final part of our VPC deep dive, and so far I think we've done pretty well. We've built our cloud kingdom, figured out how to secure it. We even connected it to some other kingdoms.
Yeah, we have covered a lot of ground. It's true. But there's one more piece of the puzzle that I think we should explore: VPC endpoints.
Ah, yes, those hidden passageways you mentioned earlier. They let us connect to AWS services privately without going over the public internet, right?
Exactly. VPC endpoints provide a secure and efficient way to access services like S3 DynamoDB or even API Gateway, all while keeping your traffic within the AWS network.
So it's like having a secret back entrance to these services just from my VPC.
Aha! You could say that. And remember, there are two main types of VPC endpoints: gateway endpoints and interface endpoints. Each has its own strengths and use cases.
Right, I remember you mentioning that. Can we break those down a bit more? When would I use one versus the other?
Absolutely. Let's start with gateway endpoints. They're specifically designed for S3 and DynamoDB. The setup is incredibly simple. You just add a route in your VPC's route table, pointing traffic destined for S3 or DynamoDB to the gateway endpoint.
So it's like adding a new traffic sign in our VPC, directing traffic to a dedicated lane for S3 or DynamoDB. Does this mean I don't need an internet gateway or NAT gateway if I'm using a gateway endpoint for these services?
You got it. Your traffic stays entirely within the AWS network, traveling directly to the service. No need to go out to the public internet and back.
That's a huge win for both security and performance. No public exposure and less latency. But what about those other services? That's where interface endpoints come in, right?
Exactly. Interface endpoints are used for accessing most other AWS services besides S3 and DynamoDB. Think of things like API Gateway Kinesis or even SQS.
Okay, so they cover a wider range of services. But
Right.
how do they actually work? Is it the same simple route table setup?
So interface endpoints are a bit different. Instead of just being a route table entry, they actually provision a network interface or an ENI within your VPC.
An ENI. That's like a virtual network card for my VPC, right?
That's a good way to think about it. This ENI has a private IP address within your VPC, and it acts as the entry and exit point for traffic going to and from the service.
Ah, so it's like having a dedicated private connection to the service. That makes sense. But what about security? How do I control access to these interface endpoints?
Well, that's where our trustee security groups come back into play. You can attach security groups to your interface endpoints, just like you would to an EC2 instance.
So we can use those familiar security group rules to control exactly which traffic is allowed to reach the endpoint.
That's great.
It feels like everything we've learned about VPC security is coming together now. We've got security groups, for instance, NACLs for subnets, and now security groups for interface endpoints. It's a complete security ecosystem.
You're getting it. And this highlights a key point. You have an incredible amount of control over security within your VPC. AWS gives you all the tools you need to lock things down and ensure that only authorized traffic can reach your resources and the services they depend on.
This has been incredibly insightful. I feel like we've gone from VPC novices to having a pretty solid grasp on how these things work.
Me too. But there's one last thing I think we should touch on, something that can give you even deeper insights into your VPC traffic. Flow logs.
Flow logs,
Mm.
those were the security cameras of our VPC, right?
Yeah.
They capture all the network traffic details.
Exactly. Flow logs provide a treasure trove of information about every network connection in your VPC. They record source and destination IP addresses, ports protocols, timestamps, and even the actions taken by security groups and NACLs.
Wow, that's a lot of data. But data is only useful if you can make sense of it. How do we actually analyze these flow logs?
Well, you can send your flow logs to either Amazon S3 for long-term storage or CloudWatch logs for real-time analysis and alerting.
So I could use command line tools, scripts, or even visualization tools to dig into that data and look for patterns or anomalies.
Absolutely. And you can even set up alerts to be notified if something suspicious is happening in your network. It's a really powerful way to monitor and troubleshoot your VPC traffic.
Flow logs sound like a must-have for anyone serious about VPC security and performance. This has been an amazing deep dive. We've covered so much ground, and honestly, I feel like we could build just about any network architecture on AWS now.
I agree. We started with the basics and gradually built up our knowledge, exploring everything from subnets and routing to security and hybrid connectivity.
And it's incredible how much control and flexibility AWS provides. You can really tailor your VPC to meet your specific needs.
That's the beauty of the cloud. It gives you the power to design and build the exact infrastructure you need without the constraints of traditional data centers.
Well said. So to all our listeners out there, I encourage you to keep learning, keep experimenting, and keep pushing the boundaries of what's possible with VPCs. It's an exciting world to explore.
And remember, a well-designed VPC is the foundation for a secure, scalable, and successful cloud deployment.
Until next time, happy cloud networking.